Frames that are like flat, yeah. Oh wait, we need to.
Not that one, because that one goes to 0.
No, we want to see that.
You want to see this one?
Yeah.
They can't go
Just
to
do
0.
all of them.
So, so it looks like it changes somewhere out there. Yeah,
It goes away from being a sine wave.
Right. So blue
To
blue is X. So that's prey. That's rabbits. Rabbits very rare. So the fox population is decreasing.
Yeah.
Fox population decreases enough so that the rabbit population starts to rebound. The rabbit population is growing, and then the foxes they're going to catch up.
And then it would make sense if they started looking like a more standard
Yeah,
ghost that after that, but I don't know for sure. We'd have to.
Well, right. It's not exactly, but that might make a big giant orbit.
Right.
Right, like we were talking about.
Are there like other foxes coming into the same habitat or something?
Yeah, it's interesting because it looks like the foxes die out.
Right.
Yeah.
Maybe there's just
Well, but
two.
Well, yeah.
Here's a half of
There's
a
zero.
It's just one leg and 3 tail feathers.
Well, like if there's not enough food to support the foxes, then the foxes would go away because they're just physically not.
Technically, if once they hit 0, they're not coming back.
Well,
Mathematically,
once they hit 1, right? If
Well,
you have
it's a
1
different-
rabbit,
Yeah,
Haven't you seen Jurassic Park?
Effectively 0 in a population model. That's the
right.
funny-
So I'm gonna go back. I'm gonna refer back to the original assumptions and say that the assumptions are very crude.
Yeah.
So does this accurately portray competing populations? No, because it's a closed system. The predator only feeds on that one species. In the absence of that species, the other one would explode, go to infinity, regardless of everything else that's happening. So it cuts out a lot of other factors, of course.
And also like infinite.
But it's a good start.
Infinite amount of food for the prey.
Oh,
Limited.
Right. Well, wait. You could get rid of the infinite amount of prey by just making it a triple system, right?
Well, I mean,
Like having-
it would
like
have to
having-
do with food.
Right. Well, no, but like the prey would be dependent on the food, right? So you just have like a third X sub 3 representing the prey's food eating its food. Yeah.
But then also volume of the actual area of where you're. I mean, how fast they're interacting and how far are they going.
Right.
What about
But
a model
that's all
that
it
takes
costs.
in like natural lifespan into account?
Right.
Wasn't
Yeah,
that
a more accurate model would have to take that into account.
Or like
It would have to take into account amount of space, land that's available. Is there hunting?
what about like having
You get tired.
requiring at least 2 of one species for it to continue? What about requiring like a male and female?
Yeah. So another thing about a model is there's a trade-off. All right. So there's a trade-off. You want it to be accurate, so you have to add some things into it. But the model also has to be manageable. So if you try and put every factor into it, it may just be so wieldy that you can't do much with the model. So it has to be accurate enough to tell you something useful, but also simple enough that you can work with. Yeah. So a lot of times they are idealized models. Okay. But yeah, there's a lot of money in accurately being able to model stuff, and most of that stuff's done with computer simulation. Throw in these variables. Same thing is true if you've taken a lot of stats. If you've done what's it called? Regression, linear regression. You want all these factors. Say you want to explain the average CEO pay. You randomly choose a CEO. Maybe there's all these factors that go into it: age, gender, how long they've been working, what kind of business it is. You want to put in all these factors, and they might help you to explain what's actually happening. But the more you throw in, it makes the system a lot more wieldy. So if it's extraneous, if it doesn't give you much more accuracy, then a lot of times you just do without that factor. You know what I mean? Just in the trade-off for being able to work with that model. All right. So one thing we can do with this, how much time? We got a little bit of time. One thing we can do with this is we can find the equation of the trajectories explicitly. Or, sorry, implicitly. so we had these two, those two equations, dx dt, dy dt.
You have a box on this thing?
That goes one of them.
Okay. So let's do this. Dy dx. I can, and we did a little bit of this last time. We can, there's a way to remove oftentimes that parameter t. It's called eliminating a parameter. I can write this as dy dt over dx dt. And hey, we have expressions for both of those. Dy dt was what? Wait. Yeah. It was negative 2y plus xy. And we factored that. Let's do it in factored form. How about negative y? Or just, you know what I'm going to do? Well, we'll do that in the next step. 16 minus 2x, that was dy dt, over dx dt. Dx dt is x 4 minus y. All right, one more step. I'm going to push that negative 1 into this term. And so I got y and 2x minus 16. That just reverses the order of the fraction. Over x times 4 minus y. Okay. Notice something about this. This equation is separable. We did a little bit of this last time. So what this looks like is, where's the y is going to go? I'm going to have dy over y and 4 minus y up top. 4 minus y over y dy equals, and how's the x is going to go into this, multiply, it's going to be 2x minus 16 over x. Dx. Yeah? So, let's integrate this. Integrate both sides with respect to the corresponding variable. And what do we get? Oh, we can break this up. 4 over y minus y over y equals integral of 2x over x, that's just 2, minus 16 over x dx. All right, so what do we get when we integrate the left side?
4 times the natural log of y minus y.
4 natural log of y minus y, plus some arbitrary constant, but I can collect constants on one side. And over here we get 2x minus 16 natural log x, plus some constant of integration c there. Okay. So, getting everything over to one side, we can write this. This is an implicit equation. There's no way to solve this for y, because I got y here and I got y also as the argument of the log function. There's no way to solve that in any closed explicit form. But we could write this as 4 natural log y minus y plus 16 natural log x minus 2x equals c. Okay. So this is an implicit equation for that graph. So say, for instance, say 10, 6 is initial population at some time. Then we can use that to solve for the value of c, yeah? Oh, and I solved it and I didn't write it down.
Where'd you get 10-6?
I just made it up. So I'm going to clear out this. Let's get a new phase plane. There we go. So say 10-6 was just some initial population. So 10 x's would be like rabbits. 10 rabbits, 6 foxes, or 10,100 and 600, or 10,000 and 6,000. And there's our curve. And what we have there is the equation of that curve in implicit form. If I solve for C. C would be equal to, yeah, just 4 natural log y, that's 6, minus y, plus 16 natural log of x, minus 2x, that would be 20. And I think I got it down. 18.
Yeah, 18.0084 is what I got.
So that would be the equation of that particular curve. Yeah. Oops. Yeah. There we go. All right, and the other cool thing to think about, and since we're talking about Calc 4 over here to begin with, is that if I isolate this part on the left, this constant on the right, this could be thought of as a level curve.
Yes.
Level curve, constant C of this function of x and y. So if this is some capital F, not little f or little g, but if this were some capital F, some function of 2 variables, then that describes the relation, I'd get a surface, right?
That's why I thought we were going to R3 with this.
Right. So this would be the level, this would be, when C is 18, we get that level surface. That would be a cross-sectional slice of this surface parallel to the xy plane. And different values of C would correspond to different level surfaces or contours. So you can imagine 3 dimensions, those are just level curves of a surface. Probably some sort of sloping down paraboloid
Or hill, or
valley.
Well, yeah, well,
And that would be the maximum or minimum point.
because that's right there is 0, 0 on for the derivative, so that means that's where it's not changing.
Oh yeah, dx dt is 0,
plateau
dy
or it's
dt is 0, so that's either a max or min
Yeah.
of that of this surface. Okay. All right, we're gonna do one more example and call it quits today. All right, let's minimize again. All right, so one more example. And this is going to be so that's not the only model out there. This one's going to be non-Lotka Volterra. So what we're going to do is page 409. This is in the homework. 409, numbers 12 and 13. All right. So say we have this model, dx dt equals 5x minus x squared minus xy, and dy dt equals negative 2y plus xy. All right, so one, you might be able to tell right off the bat, since every term involves a variable 0, 0, would make this would be a critical point. I'm going to call this equation, we already used 1 before, let's call this equation 2. So 0, 0 is a critical point. And how would we find the others?
If we just factor out the common piece.
Yeah.
If you said dy dt equals 0, you get x equals 2.
If you said what?
Dy dt equal to 0, then you get 0 equals, and you can factor.
Well, you could factor a y out of that one, so it'd be y times x minus 2. So yeah, y would have to be 0, or x would have to be 2. So you could solve that one. That would be the one to attack first, because you could factor a y out of that cleanly. So y would have to be 0 or 2. Sorry, y would have to be 0 or x would have to be 2. Yeah, that would work. And then take those one at a time. If y is 0, obviously that whole thing is 0. So that doesn't tell you anything new about x. But
Oh, that's weird. Y is 2.
if y is, if x is 2, then you can solve that equation for y. Okay. The other way to do it, this is what I was expecting when I asked that question. The mighty TI, right? You guys can solve this because even if it's nonlinear, you can use the solve routine, right? F2 algebra. You can have the calculator solve this equation. Type it in, 5x minus x squared minus xy equals 0, and you have to have the word and the second equation equals 0. Solve for x and y in brackets, and you can solve a system like this. Okay, so that's kind of trivial. But 0, 0, and when x is 2, you can find out what y has to be in that other equation. So it can be shown that the system has 3 critical points. 0, 0, 5, 0, and the non-trivial 1, 2, 3. So 2, 3 is definitely a non-trivial solution to that. And again, when x is 2, you'd solve that and you get y equals 3. Okay? Or I'm going to make a note so for your final exam or something, use the solve feature in your TI. Okay. All right, so we need the Jacobian. And what's that going to be? So Jacobian, that's our little f. Yeah, so again, sear it into your brains, f sub x, f sub y, g sub x, g sub y, where those two functions are dx dt, dy dt. All right, so derivative with respect to x. I'm going to get 5 minus 2x minus y. That's one entry in this matrix. And then the same function, differentiate with respect to y. 0, 0, and negative x. All right, so second function with respect to x. First term's gone. This one is just going to be plus y. And then with respect to y, I'm going to get negative 2 plus x. All right, so there's the Jacobian. These problems actually come 11, 12, 13. It asks you to analyze all 3 of them. But we're just going to start with the 0.50. So this is number 12. So that Jacobian at 50, gotta be careful. 5 for x, 0 for y. That would be 5 minus 10. That would be negative 5. Opposite of x, it's also going to be negative 5. Y, that's 0. And negative 2 plus x. That's going to be 3.
Questions? Oh, so what are we trying to solve for? Like, is it a population or something?
Oh, we're gonna categorize. It says to show that these are a certain kind of critical point.
Okay, so it's not necessarily a population.
Not so much. 50 would be boring.
That's
2-3 would be the interesting, non-trivial.
That's why I was asking what type of thing this was.
Yeah.
Otherwise, I would assume that
Yeah.
we just.
So what does it specifically actually ask for?
Which
Show
problem
that
is
the
it?
linearization of 450 is u prime equals negative 5u minus 5.
Okay. So that's the first part of it. So u prime
Which problem is this?
This is number 12. So -5, 0, 3. And this is, we've taken it to UV deal. This is UV. So therefore, you could say U is, or this is prime again, U prime, V prime. -5 U minus 5 V. And V prime would be 0 U plus 3 V. U plus 3V, so put the 3V right there. And number 12 asked us in 6.3, show that the linearization is U prime equals -5U minus 5V, and V prime equals 3V. Okay, got that. Then show that the coefficient matrix of this linear system has negative eigenvalues, blah, 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 hence 5, 0 is a saddle point. All right, so they tell you the conclusions that you're supposed to come up with, and we got to show that. So let's finish off this problem. This is our Jacobian matrix. We just need the eigenvalues. All right, so hopefully you're getting used to this enough. This Jacobian, this matrix minus lambda times I, it looks like -5 minus lambda on the diagonal, 3 minus lambda, and when we find a determinant, -5 minus lambda times 3 minus lambda minus the product of the other diagonal. That's just 0. Okay, so I'm going to pull out these minuses because I hate all these negatives. Pull a negative out from each factor, and they cancel with each other. I would have 5 plus